In a metal conductor, the positively charged particles are fixed in place, whereas the negatively charged particles, called electrons, are free to move around. A metal typically has an equal amount of positively and negatively charged particles, making the metal as a whole electrically neutral. If we apply a force trying to push extra electrons into this metal plate, we will not be successful, because particles with the same charge repel one another. If extra electrons accumulate inside the metal plate, they will repel each other and repel any of the new electrons trying to enter. Therefore, even if we apply a force, the metal will remain electrically neutral. Now let us consider a new scenario where there is another metal plate close to the one shown. As electrons accumulate in the first metal plate, they will repel the electrons in the second metal plate. The positively charged particles left behind in the second plate will exert an attractive force on the negatively charged particles in the first metal plate. This makes it possible for the first plate to have more negative particles than positive particles. As we add electrons to the first metal plate, an equal number of electrons leave the second metal plate. After a certain number of extra electrons accumulate on the first plate, they will repel any new electrons trying to enter. The first metal plate has developed a net negative charge, and the second metal plate has developed an equal and opposite net positive charge. We can cause this equal and opposite charge on each plate to be larger by applying a larger external force. If we remove the external force we are applying, the extra electrons in the first metal plate will continue to repel one another. We have now returned to our original condition where the net charge on each plate is 0. The two metal plates are what we call a capacitor. Note, voltage is shown upside down in this video because the blue arrows will show electron flow. By briefly connecting the capacitor to a battery as shown, the two plates have developed equal and opposite charges. If we then connect the capacitor across the light bulb, all the extra electrons in the negatively charged plate will move to the positively charged plate through the light bulb. If we use multiple batteries in series, then we can force the two plates of the capacitor to develop larger amounts of charge. When the capacitor is charged, its voltage will be the sum of the voltages of all the batteries. Charging the capacitor to a higher voltage will cause the light bulb to stay on longer when the capacitor discharges. Now suppose that we increase the areas of the two metal plates. This increased area allows us to push more extra electrons into the first metal plate and remove more electrons from the second metal plate without applying a larger external force. When a larger capacitor is connected to our battery, it'll take longer for the capacitor to charge to the voltage of the battery. Although the final voltage is still equal to the voltage of the battery, for a larger capacitor, this voltage represents a larger amount of charge on the two metal plates. The larger capacitor will take longer to discharge through the light bulb, thereby allowing the light bulb to stay on longer. Suppose that we add a special material in between the two plates. This material does not allow any particles to flow through it, but it contains molecules that change their orientation based on the charges of the two plates. These molecules exert forces that attract more electrons to the negative plate and that repel more electrons from the positive plate. The presence of this material has the exact same effect as does increasing the areas of the two metal plates. This allows the two plates to develop larger net charges for the same amount of applied voltage. We say that we've increased the capacitance of the capacitor. There is also a third way to increase the capacitance of a capacitor. This is by moving the two metal plates closer together. Because the two plates are now closer together, they exert greater forces on each other's electrons. This attracts more electrons to the negative plate and repels more electrons from the positive plate, allowing the two plates to develop larger net charges for the same amount of applied voltage. This has the same effect as inserting the special material and as increasing the areas of the metal plates. To create the largest capacitance possible, we want to make the areas of the plates as large as possible, insert the special material in between the plates, and move the two plates as close together as possible. The larger the capacitance, the more energy will be stored for the same amount of voltage. Much more information about electric circuits is available in the other videos on this channel. Please subscribe for notifications when new videos are ready.